for coming to the Fall Technical Conference webinar series. A couple of notes for you today. Please keep your microphones muted so we don't have any background noise. Feel free to ask any questions in the Q&A box and we'll read those off at the end of the talk. The Fall Technical Conference is a joint conference sponsored by the American Society for Quality and the American Statistical Association, with the goal of engaging researchers and practitioners in a dialogue that will lead to more effective use of statistics to improve quality and foster innovation. And the website for that is at the bottom of the slide here, so you can look up more information and the other talks that will be going on. It will be back in person next year, hopefully. It's planned to be in person in Utah, so it'll be a great place to get together. The theme there will be mining for quality with statistics and data science. Here's a list of the other talks. We're pretty early in the webinar series. So next Wednesday is the next talk. The talk today is for the winner of the Soren Bisgaard Award. This is awarded annually to recognize the paper in the ASQ journal Quality Engineering with the greatest potential for advancing the practice of quality improvement. So that paper that was chosen this year is called, the title is The Bayesian Probability of Agreement for Comparing Survival or Reliability Functions with Parametric Lifetime Regression Models. And you can see the 4 authors that contributed to that paper, and Nathaniel is with us today to discuss that topic. He is an associate professor, assistant professor of statistics at the University of Waterloo. Prior to that, he held a faculty position at the University of San Francisco in the mathematics and statistics department. He does research in the field of data science and industrial statistics, and he has a number of publications. And we'll be lucky to hear from him today. So with that, I will hand it over to Nathaniel. Thank you.
Thank you, Jennifer. Let me try to share my screen here. Okay, hopefully you can see that. Thank you, everyone.
Nathaniel, you just accidentally muted yourself.
Can you hear me now?
Good to go.
Okay, all right. I was just saying thank you, everyone, for joining today, both those of you who are here live and anyone who watches the recording later. I want to begin by acknowledging that, as Jennifer said, this is joint work with my collaborators Lulu from the University of South Florida, Christine Anderson-Cook from Los Alamos National Lab, and Steve Ringdon from St. Louis University. On behalf of all of us, we want to thank the Bisgaard Committee for giving us this honor. It really is a tremendous honor to receive this award. The next thing I want to do before getting into the main talk itself is just to sort of talk for a minute about Soren Bisgaard. I didn't have the pleasure of knowing Soren. He died in 2009 after a battle with mesothelioma. From everything I've heard from people who did know him, though, it sounds like he was a wonderful man. He was certainly an important and impactful statistician. He started out as an engineer, earning master's and bachelor's degrees in engineering and then a PhD in statistics. He's a prolific author in the field of quality engineering and industrial statistics. He worked sort of on everything, really, DOE, SPC, Gauge R&R, Six Sigma, all of it. And his impact and his importance was recognized by almost all of the major awards that we have in this field: the Wilcoxon Prize, the Schul Award, the Brumbaugh Award, the Schuhart Medal, the George Box Medal, as well as ASQ and ASA fellowships. He was also, as I understand, very instrumental in establishing NBIS, the European Network for Business and Industrial Statistics. So it really is an honor to receive an award that's the namesake of this really important and really impactful statistician. Okay, so where are we headed today? I'm going to spend a couple minutes at the outset just sort of describing the problem we're trying to solve with our methodology. And before getting even into that, I want to spend a few minutes talking about the idea of practical equivalence, because our methodology is really rooted in this understanding that two things don't have to be identical for them to be practically equivalent. And that's a sort of key component of all of this. So I'll briefly talk about that before introducing the Bayesian probability of agreement, which is our solution to this problem. We're going to compare lifetime regression models through the Bayesian probability of agreement. I'm going to illustrate that with a couple examples, and then we'll end with a quick summary. Okay, so the general problem, as I said here, is that we're comparing basically lifetime distributions, and we're going to compare these distributions in two different populations. And this general problem is important in a variety of fields. For example, in reliability engineering, where we might want to compare two different versions of the same product, say an old way of manufacturing that product versus a new one, and we want to understand whether the reliability is the same between those two versions. This is also really relevant in survival analysis, where you might want to compare survival experiences across two different arms of a clinical trial. It's also useful in customer analytics, where customers might want to understand customer churn and compare retention curves for different customer cohorts. So it's a very broadly applicable problem. And the solution that I'm going to talk about today is useful in any of them, but we're going to really focus on reliability engineering. So the common goal, no matter which of these application areas, is generally speaking to compare two lifetime distributions where the goal is to evaluate their similarity. And the contextual goal, as I said, of today, we're going to focus on reliability context. But if you read the paper, we do also have an example from sort of the healthcare, the medical context as well. So you can read that in more detail if you're interested. Okay, so just to help you visualize the problem, I'm going to introduce one of the examples now, and we'll kind of refer back to it a couple times throughout this talk. And it's this accelerated life test that was investigating a particular component of a toaster. The component is called the snubber, and the snubber is the part of the toaster that keeps your bread from hitting the ceiling. So when you're toasting your bread and it's done, it pops up. And there's a spring that is sort of mediating that ejection. The snubber is dampening that ejection force. If the snubber wasn't there, your toast would hit the ceiling. Obviously, you don't want that, so you want a snubber that reliably dampens the spring that's ejecting the toast. So that was the component of these toasters that were sort of under comparison. So two different versions of this toaster based on new versus old versions of these snubbers. And so the experiment itself had 52 old toasters, 54 new toasters, and their lifetimes were evaluated by exercising the ejection mechanism and hence the snubber many times. So the data is reasonably small. We can just tabulate it all here. You'll notice that there are censoring times. Not every failure or not every snubber was observed to fail. Many of them, got, for example, over 1,000 cycles with no failure. So this is sort of the kind of data we're dealing with here. Here's a visualization of this data. So on the left-hand side, we've got the event data for the old toasters. The filled-in circles are actual failures. The open circles are censored observations. And on the right-hand side, we have the same information, but for the new toaster. And so generally speaking, we're trying to compare this data, these distributions. We want to understand if this new snubber improves the lifetime of or I guess the new process of manufacturing this snubber creates more reliable snubbers that last longer. And generally speaking, just by looking at these graphics qualitatively, it does seem like the lifetimes in the new snubbers on the right-hand side are a little bit longer than on the left. So it would suggest that these the new Snubber is more reliable. But this is the kind of problem that we're trying to solve here. We want to compare the reliability of two different versions of a product. Okay, so with that sort of context set, let's talk for a couple minutes here about practical equivalence. And this is something that almost everybody who teaches an intro stat class will mention when you first talk about hypothesis testing. You talk about p-values, you talk about statistical significance, and you generally acknowledge that just because an effect or a difference might be statistically significant, that doesn't imply that it's practically important. We almost all say that, but that's also generally where that conversation stops. And what we're doing here with this methodology that we've developed is to really put this idea of practical equivalence at the forefront and incorporate it into the analysis. So ordinarily, these kinds of comparisons are done with just regular hypothesis tests. They might be some sort of a two-sample test like Mantel-Haenszel log rank test, that sort of flavor of a hypothesis test. It might also be a hypothesis test in the context of some sort of a regression model, where maybe you have a term that distinguishes one version of your product from another, and you want to see whether that term is significant. But generally speaking, the approach to addressing this problem or answering these questions is through some version of a standard hypothesis test. And these kind of hypothesis tests, generally speaking, the null assumption is that the two things you're comparing, these two groups, are the same. And then with the data you collect, you're searching for evidence to reject that null. You're looking for evidence of dissimilarity. And that is kind of fundamentally problematic, especially in situations when you have a lot of data, because as we all know, with enough data, any difference, no matter how meaningless that might be found to be statistically significant. And so there's this sort of counterintuitive thing with power here, where with enough data, you're always going to find a significant difference. And so instead, what seems more reasonable is to kind of flip around that baseline assumption and assume at the outset that the two things are not the same. And then the data you're collecting is trying to help you gather evidence to show that they are similar, that they are equivalent. And there's a whole other class of hypothesis testing that is sort of born out of this philosophy referred to as equivalence testing. You may or may not have heard of it. There's a reference there if you'd like to read more into that. But the idea here with equivalence testing, or what we're doing here today, is that there's this sort of fundamental philosophy that two things don't need to be identical for them to be practically equivalent. And so what that means is that we kind of have to acknowledge and recognize that there's a size of difference that matters and a size of difference that doesn't matter. If we're thinking about our toaster example here, let's think about you've got your old Snubber. Let's say that it has some sort of a guarantee, like you can use it 1,000 times, and after 1,000 times it might start to break down. And then your new version, or say a different brand of a product, they guarantee 1,100 toasts before it starts to break down. Is that 1,000 versus 1,100? Is that meaningful? That difference of 100 additional toasts? Maybe it isn't. Context dictates that, but if there is that sort of a threshold between a practically important difference and a practically unimportant difference, it seems logical to try to incorporate that into the analysis, and that's what we're trying to do here. And this sort of class of methodology is becoming more popular. I'm sure, as all of you are aware now, we're kind of in the midst of this p-value controversy and reproducibility crisis. The American statistician a couple of years ago had this whole special issue devoted to this problem. The ASA put out a statement sort of encouraging the statistical community to try to think about alternative ways of sort of doing decision-making in the context, or in the face of uncertainty, by means other than traditional hypothesis tests, trying to account for context and this idea of practical importance versus statistical significance. And so that's sort of where we're coming from with this Bayesian probability of agreement stuff. So in particular, what we're doing is that we're going to propose a methodology for the comparison of parametric lifetime regressions that explicitly sort of accounts for this idea of practical equivalence, and we do it from a Bayesian estimation standpoint. Okay, so that being our context and our sort of motivating paradigm, the solution is based on something called the probability of agreement. And this is, as you'll see in a moment, a reasonably simple, but I think very useful idea. And we're not the ones, well, this paper isn't the paper that sort of was the genesis of the probability of agreement. This has existed for a couple of years now. We're just adapting it to this context of comparing lifetime distributions and with censored data. So generally speaking, the way the probability of agreement works is you imagine you have two things you want to compare, two characteristics, let's call them theta 1 and theta 2. And the idea is to decide whether theta 1 and theta 2 are similar. In particular, are they practically equivalent? And oh my goodness, there's a cat here to say hello. We want to identify whether they're practically equivalent or not. And so we do that by quantifying the likelihood that they are practically equivalent through this probability that the difference, the absolute difference between theta 1 and theta 2 is less than some threshold delta. And so this delta is referred to as the equivalence margin. It's this sort of, you can think of it as the threshold between differences that are practically important versus unimportant. And so this region, plus or minus delta, you can think of that as like an indifference region or a region of practical equivalence where any differences that land in there are just considered practically negligible. They don't mean anything. They're not practically important. And so what the probability of agreement does is it just quantifies what's the probability that happens, that these two characteristics, theta 1 and theta 2, whatever they are, what's the probability that they are practically equivalent. And so it's very intuitive and very flexible. So theta 1 and theta 2, it can be almost anything. And the way we interpret this, no matter the context, no matter what theta 1 and theta 2 are, no matter how this probability is calculated, the interpretation is always super straightforward. It's just the probability that these two things are practically equivalent. Values close to 1 are going to sort of suggest strong agreement. Values close to 0 are going to signify disagreement. And so, as I said, this isn't new. This has been applied elsewhere. It began where it first started was with the comparison of measurement systems. So, in context of gauge R&R type studies, imagine you've got a new measurement system. You want to decide whether it works as well as an existing one. We can use a probability of agreement in the context of a specific measurement system comparison study to make that decision. We've also applied it in areas where we have interest in comparing fitted and predicted generalized linear models. Also the comparison of sequential experimental results in the context of response surface methodology. So that this general idea of this probability agreement is quite versatile. And what we're doing here with this particular work is just imagining that theta 1 and theta 2 are some sort of a quantification that summarizes the two lifetime distributions that you want to compare. And through this metric, we're going to quantify the likelihood that these things are practically equivalent. Oops. And in this setting, theta 1 and theta 2, they are going to be parameters or functions of parameters of these lifetime distributions. And so the comparison that we're making, this probability that we're calculating, it really makes the most sense to do this through the lens of sort of the Bayesian framework. That way, it really allows for intuitive interpretation. The conclusions that we draw are on or are with respect to the things that we care about, these particular parameters, theta 1 and theta 2. So there has been work done in these sorts of comparisons in frequentist paradigms, but for what we're talking about today, the Bayesian framework seems to make the most sense. So what that does is it sort of leads us to this version of the probability of agreement known as the Bayesian probability of agreement. And Christine and Steve and I have done work in this area before. We sort of started thinking about this as a means of comparing generalized linear models. But the innovation and the novelty here is to adapt that to lifetime regression models, and specifically handling sort of the reality and the nuances that go along with censored data in these sorts of settings. So the BPA, Bayesian probability agreement, is the same idea, same general philosophy behind this probability calculation, but it's a posterior probability. So given some data, given prior beliefs, we put all of this together with sort of an assumption about the data's distribution, and we get the posterior, and with that posterior, we calculate this quantity. And as before this, delta is the equivalence margin, so plus and minus delta is the region of practical equivalence. And we interpret this in exactly the way that I just talked about on a slide or two ago. So just sort of setting some notation and terminology, we're gonna let T be this random variable that represents the lifetime of a particular unit in one of our two groups. And this lifetime distribution F, in our paper, we consider three different distributions: Weibull, lognormal, and gamma. But the probability of agreement and the way it's calculated, and specifically, as I talk about in a second, we use MCMC. We can basically accommodate any distributional assumption that you want to make, but we highlight these three in the paper. Okay, so then with that as our context, our lifetime distribution being something like Weibull, lognormal, or gamma, let's talk about what the theta is. You know, I said previously that we want to choose theta in a way that, you know, it's something that usefully describes or summarizes the lifetime distribution. And so this can reasonably be anything, but the two particular sort of versions of theta that we think about here are the first one that you see on the left. This is just your classic survival or reliability probability. So that's one way of summarizing the lifetime distribution. And so that's one version of the problem that we're going to deal with today. Another one is where the way we want to summarize this distribution is with a quantile or a percentile from. You know, maybe we want to compare these toaster snubbers in terms of sort of worst case scenarios, maybe 10th percentile, the 10th percentile of their lifetime distributions. You want to make sure that you know, in a worst case, the snubber at least allows you to do, say, 500 toasts before it starts breaking down. And maybe that's the way we want to do the comparison on the basis of percentiles. And the nice thing about, or one of the nice things about the Bayesian probability of agreement is that we can really easily and flexibly accommodate any sort of function of the parameters of these lifetime distributions. So as I said, these are the two we're going to focus on. But if you had some other summary that you're interested in, maybe it's the mean or some measure of variation, we can handle all of that. And as you can see in those two particular specifications of theta, those thetas themselves are functions of some input. In the case where theta is the reliability function, it's a function of time or of a lifetime. In this case, in the snubber example, we're talking about numbers of cycles. So theta there is a function of t. In the case when we think about comparing percentiles, theta is a function of that probability p. We might also have other covariates that we want to incorporate into our analysis, in which case theta is also going to be a function of those. And so what this means is that our analysis should try to account for all of these things and take all of these context-dependent covariates and information into account. So what we're doing, generally speaking, is a comparison of lifetime regressions. And so theta 1 and theta 2, as you see in this bottom bullet here, they're just some function of a linear predictor of the data that you happen to observe in your context. And the form of that function h depends on things like which lifetime distribution have you chosen, and hence which length function sort of defines your GLM. It also is a function of which specification of theta have you used. Are you talking about a reliability function? Are you talking about a percentile? But generally speaking, theta 1 and theta 2 are some function of a linear predictor, and we want to compare those. And the nice thing then is that we can really tailor our analysis to our particular context and particular regions of interest in this input space. And draw conclusions about the comparability of the lifetime distributions in sort of across settings that we're interested in. And we don't need to limit ourselves to a single conclusion, yes or no. Are these two things similar? Are they practically equivalent? We can have a more nuanced discussion about, well, maybe they're equivalent or practically equivalent for some values of the input space and not others. And so it really provides a nice sort of flexible means of a sort of a nuanced analysis. As I said, the interpretation is quite straightforward. It's just a probability. The nice thing about that, I think, is that even for practitioners who may not be statistically savvy, that is still easy enough for them to interpret. What's the probability that these two things are practically equivalent? And unlike a p-value, well, so what I was going to say is that what we're finding nowadays, with this misuse and misunderstanding of p-values, is that often people misinterpret that p-value as being the probability that the null hypothesis is true. Of course, we know that's not the case, but this probability of agreement gets a lot closer to that kind of intuitive interpretation, and so I think that it's really user-friendly in that way. There's a couple sort of user-specified choices that need to be made here that helps make it sort of an analysis that can be tailored to a particular context. For example, how big does that probability of agreement need to be in order for you to believe the statement that these things are practically equivalent? That's something that the user can decide in sort of in a way that is I don't know, congruent with their own risk tolerance. Likewise, this choice of the equivalence margin delta, that's something that they should choose, and that they should do so carefully. As we'll see in the examples I'll talk about in a minute, your conclusion is directly driven by how big delta is. And so it's important that you've chosen that so that the conclusions that you provide or conclusions that you make are meaningful in your context. So how do we calculate this? As I said, it's just a posterior probability. So given the data, if we've got our, where's my cursor? We've got our event times, we've got our censoring indicators to indicate whether the event time was a failure or a censored observation. We've got these covariates. Given all of that data in the joint posterior for theta 1 and theta 2, this is just a posterior probability. That integral is easy to write down, but not very easy to calculate, certainly not analytically, and even numerically, it can be unstable. So we've opted to go the route of MCMC to do the estimation. Not only does it just make the process easier, it also very easily allows for flexibility in terms of what data distribution are we assuming for that lifetime distribution, what prior distribution assumptions are we making, how do we choose to specify these thetas. MCMC just really nicely handles all of that. And so in that case, the way we estimate the Bayesian probability of agreement is just to take posterior draws from the posteriors for theta 1 and theta 2, and then just look at what proportion of them, these sort of paired differences, are practically equivalent. Are they less than or equal to delta? And that's very simply how we calculate this. A little bit more information about these posterior draws. What we're actually doing is taking posterior draws from the posteriors for the betas in these regression models, and then sort of plugging that through this expression for the thetas, these functions, H functions, and through that we get our posterior draws for the thetas themselves. N here is the total number of posterior draws that we retain that we actually use to estimate the posterior distributions. We do some burn-in, we do some thinning to make sure that we've reached the steady state of these Markov chains, and that there isn't serious autocorrelation. So our estimates of the posteriors are reasonably accurate. Just a couple comments here about the priors. For the betas in these regressions, in our analysis and the way we presented it is just to basically come at this in a very uninformative way. We choose very diffuse priors, but obviously you could change these assumptions based on your own context knowledge and your own prior beliefs. If you want to read about it in more detail, there is a sort of a simulation that we do in the paper where we investigate the choice of the prior. As you might expect with a lot of data, the prior choice doesn't make much difference, but for small amounts of data, it does. As you know, it almost always does. But if you want to read more about that, have a look at that in the paper. Okay, so let's come back to the Snubber example. There's two examples that we're going to talk about to illustrate these ideas, but I'm going to start with the Snubber one. Okay, so just to remind you, we're talking about toasters here. The Snubber is the, if you weren't here at the beginning, the Snubber is the component of the toaster that dampens the spring that ejects your toast. So if that thing's broken, your toast is hitting the ceiling. Okay, so this was the data. The way we had sort of visualized it before, we wanted to compare these lifetime distributions. And so we're going to do it in two ways. The first one here is going to be based on a comparison of survival probabilities or reliability probabilities. So the specification of theta in this case is the survival function or the reliability function, which is what you see plotted on the right-hand side here. This was done with Weibull regression. The data sort of supported a Weibull analysis, but if it didn't, a lognormal or gamma, like we talked about a minute ago, could have been used here. What we see just sort of qualitatively by looking at this plot is that the new design seems to be better. The lifetimes seem to be longer in the sense that the probability of surviving to 2,000 cycles is higher with a new design than in the old. We see early on, though, the reliability is pretty similar. But over the long run, the new design does seem to be a little bit more reliable. And so what we're going to try to do here is formalize that interpretation and formalize this decision with the Bayesian probability of agreement. And so visually speaking, what we're doing is imagine we're looking at the vertical distance across this whole x-axis between the red line and the blue line. And we're asking ourselves, what's the probability that that difference is within plus and minus delta? And now it's not as simple though as just, is it between plus and minus delta or isn't it? Because there's uncertainty associated with these, the estimates of these curves. And so that's where this idea of probability and uncertainty comes in. So here are the BPA curves for a couple different choices of deltas. So remember, delta is this equivalence threshold. A delta value of 0.1, for example, that brown curve, I guess I'd call it, maroon curve maybe. What that means is that a difference between two reliabilities of 0.1 or less is not important, but differences larger than that, we would say that those are practically different. So if you had two reliability values like 0.8 and 0.85, those would be considered practically equivalent. 0.8 and 0.95, those would not be, those are too far apart. And so as you can see, the conclusion that you would draw regarding agreement and whether these things are practically equivalent, that's going to depend on the value of delta. And the ordering that you see here makes sense. The larger values of delta generally lead to higher probabilities versus smaller values of delta, which correspond to lower probabilities, because we're just being, we're either sort of widening or narrowing that band that defines indifference. What we see, generally speaking, qualitatively, is that as the number of cycles increases, agreement decreases. Early on here, for sort of low numbers of cycles, there's generally speaking pretty good agreement between these curves. And that matches sort of with this region here where the red and the blue curves are more or less on top of each other. But as the number of cycles increases and those curves diverge, this probability decreases. You'll notice that it starts to increase a little bit toward the end. That has to do with the fact that eventually these reliability curves are both going to approach zero. And in general, what we would expect to see if we sort of extrapolated far enough is sort of like a bathtub-shaped curve in these BPA values, sort of signifying that early in the lifetime and very late in the lifetime, the reliabilities are similar, but then in the middle is potentially where they differ. Is that everything I wanted to say about this? I think so. So that's an analysis based on this specification of theta being survival or reliability functions, probabilities. So let's also think about this from the perspective of percentiles. Let's say we want to compare the survival distributions based on, for example, the 20th percentile. If that's what I cared about, then I could compare these two estimated percentiles. Things look pretty similar there. Further in the tail of the lifetime distribution, if we wanted to look at the 90th percentile, then we're seeing a bit of a difference. And so generally, we're drawing similar conclusions here. We're just sort of looking at the problem from a different angle. The BPA in this case has sort of slightly different pattern, but also generally communicating the same information, which is that as the number of cycles increases, we generally have disagreement between the two versions. The new design seems to be better, practically speaking, than the old. One point that I think is important to highlight is that the delta value, or I should say the scale or the units of the delta value, that changes and is dependent entirely on how you specify theta. As you can see here, delta here is defined in terms of cycles, and it's just in terms of the lifetime. Whereas on the previous plot here, these deltas were probabilities. So, coming all the way back to here, this, no, I'm not gonna go back that far. I said a couple minutes ago about how choosing delta is really important and sort of being careful with that choice. This illustrates another facet of that its scale or its units depend on the way you specify theta. So what do we find? As the number of cycles increases, agreement steadily decreases, but the timing and magnitude of this disagreement depends on delta. Those curves differed slightly in terms of when they started to drop off versus go back up. We remarked how sort of in the far tails of that lifetime distribution, agreement starts to increase a little bit. And as I said, that's sort of in recognition of the fact that eventually these things will sort of always fail, and the reliability will be zero. So let's talk about another example. That first one was hopefully illustrative and sort of give you a sense of what we're trying to do here, but it was reasonably simple in the sense that there were no covariates. So I want to illustrate with this example the flexibility of the methodology in a setting where we do have some covariates. So this is a study that Meeker and colleagues wrote about, where it was an accelerated life test used to sort of assess the reliability of a spring. And as with the Snubber example, we're sort of comparing a new versus an old way of processing these springs. And ideally, what they hoped to show and hoped to find was that the new method of processing would meaningfully improve the spring's lifetime, referred to as fatigue life. And this was measured in terms of number of kilocycles sustained before failure. And so the design of this study, or this accelerated life test, had 108 springs. That's a typo. They should both say 54 old and 54 new. And they were tested up to until failure or 5,000 kilocycles, whichever came first. And this was done in the context of a full factorial design, where one of the factors is the processing time, but there's two other design factors that were of interest here. And they were processing temperature and displacement, stroke displacement. So process temperature was either 500 or 1,000 degrees Fahrenheit. Stroke displacement, which it measures sort of the distance that the spring is compressed in the test. That's either 50, 60, or 70 mils. A mils is 1,000th of an inch. I had to look that up. I didn't know. In Canada, we use the metric system, so was new to me. But so we have basically a 2 by 2 by 3 factorial experiment here. And 9 replicates were performed in each of those factorial treatments. And both the Meeker analysis and our analysis also uses a Weibull distribution to model this fatigue life. And then we include temperature and stroke displacement as covariates. So as I said, there's basically 6 cells or 6 factorial combinations here based on the different combinations of stroke displacement and temperature. And then within each, there's a comparison of new versus old spring processing. And so what we're seeing here are the reliability curves. Red is new, blue is old. The solid lines are the estimates themselves, and the dashed lines are 95% credible intervals. And so generally speaking, we're just trying to compare these. We're trying to evaluate whether the new processing method improves the lifetime, the fatigue life of these springs relative to the old. And when you look at this, I think it's quite clear that that is the case. The red curves are almost always above the blue curves, except when both reliabilities are 0. So that's one sort of thing to comment on. Another is to so the way these are organized, one row over another indicates increases in the stroke displacement. So top row is 50, second row 60, bottom row 70, and then left to right we have the low versus high temperature. And just qualitatively looking at this, we see that temperature isn't as influential as stroke, and that can be sort of formalized by looking at estimates and formal models, but that tends to be the case. And then also we see that for stroke, when these accelerating factors are at their high levels, when it's high temperature, high stroke displacement, we tend to see more failures. And what that means is that we have more precise estimates of our reliability curves. And so you can see that the credible intervals are much narrower for the high levels of these factors than the low levels. And what is going to be an important component of the BPA analysis is that level of certainty versus uncertainty is incorporated into the agreement quantification. So these are the reliability curves. These are the corresponding probabilities of agreement in each case. The general pattern that we see here is that BPA curves start at 1, they rapidly drop to 0, and then over time they climb back up to 1, and that sort of matches intuition what you see here. The red and blue curves diverge almost immediately, but eventually they come back together at that sort of 0 reliability state. So that's sort of the genesis of the general curvature that we see in these plots here. Also if you look at how quickly the BPA drops versus rebounds, that is sort of a function of what we were just talking about a second ago, which is this precision. In say the lower right quadrant of plots here, like this one, when stroke and temperature are both at their high values, we have very precise sort of estimation of those reliability curves. Whoops. In which case the drop and rebound is much more pronounced in the probability agreement versus top left here, where there's a lot more uncertainty in our estimates. And so it takes the BPA longer to sort of go down and rebound again. So it's I think a nice feature of the BPA that it's accounting for these levels of uncertainty. And so our understanding of the agreement, which should accommodate our uncertainty in those reliability estimates, is sort of coming through here in the probability of agreement. Now, that particular application, there was specific process settings that they're interested in comparing. So the existing process settings were stroke displacement of 20 mils and a temperature of 600 degrees Fahrenheit. And the question was, what is the comparability of these the new versus the old processing at these specific settings. And so with the models that we fit, we didn't observe data at these settings, but obviously we can interpolate and do an analysis on that basis. We find similar conclusions here in the sense that the new processing it seems to be better than the old in terms of increasing the fatigue life. However, the stroke displacement is only 20. That's much smaller than anything that was observed in the experiment. And so there's a lot of uncertainty. We're really extrapolating with respect to that factor. And so that's why there's two things that we see here because of that. One is that we see really wide credible intervals here, almost like unusefully wide, but we also see much larger lifetimes. Our previous plots were counted in kilocycles. This was in thousands of kilocycles. But nonetheless, we can still do this analysis. The BPA accounts for these levels of uncertainty, but still nonetheless gives us evidence to believe that the new processing approach is better. Now, one thing about this particular experiment, this particular example, is that there are very sort of discrete choices of the covariates that we can evaluate things at, and sort of all of the plots that we just looked through, they were very context-driven choices of those covariates. But if a covariate was continuous, or we wanted to look at things in a more granular way, we can do that. We can fit reliability surfaces as a function of all of the covariates that we're interested in. We can then take particular sort of slices of that and look at contours as we're doing here. The left-hand side here, this is a difference contour, so that this is a difference between the new reliability contour and the old reliability contour, and this is colored based on whether that's positive or negative difference. And then on the right-hand side, we have the BPA contour, which is what's a given spot on this rightmost contour quantifies the probability that the same spot over here is practically, whether that spot is within plus or minus delta. So I don't have time to sort of go into all of this in too much depth, but I just want to highlight that in the paper, we do a few other examples where we've got multiple covariates and we look at different ways of visualizing this kind of a comparison and this kind of analysis. So it doesn't always have to be these sorts of line plots. We can look at things in a more granular way, in a more continuous way with contours. So if that's interesting to you, please, I invite you to look at the paper. Okay, we're just about at the end. I want to leave some time for questions. So let me just quickly summarize. I think all of us on this team of authors who worked on this, I think we view this Bayesian probability of agreement as a really intuitive and practical way of making comparisons, whether that be reliability or something else, but certainly helpful in this context of reliability comparisons. It's so user-friendly. You could have very complicated assumptions about data, about these characteristics you want to compare, about the way you calculate these probabilities. But at the end of the day, the end of the analysis, that probability is so easy to interpret. It's just directly quantifying the likelihood that your reliabilities, or however you're comparing the lifetime distributions, are practically equivalent. The other thing that I think is quite nice about it is that it can be easily tailored to the practitioner's context. It's the practitioner who's deciding, how different is too different? What is that equivalence threshold in my setting? And as we've talked about, this delta, that is a big part of this analysis. We're really, as I said at the beginning of this talk, trying to put this idea of practical importance at the forefront of the analysis, not just talk about it once and say it's not the same as statistical significance, but then do a hypothesis test anyway. We're sort of proposing something that really embeds this idea of practicality into the analysis and into the conclusions. If you want to try this out yourself, we've developed a Shiny app. I'm don't think I have the time to click through this, but feel free to click this link. These slides will be available to you. This app, if you upload data in sort of a way that is formatted to be consistent with the app, it will automate everything we've talked about here today. All of the analysis, all of the plots that we looked at, it does all of that for you. So I encourage you to have a look at this. The app, within it, there's a tutorial video for how to use it. There's some example data there that you can download and play around with. So I encourage you to try this out yourself if you'd like. Okay, I'm going to stop there. And just so you know, there's a couple references here. So if you wanted to read more deeply into any of these things, you're welcome to. So thank you.
Hi, we did have a question.
Okay.
The question is, what is the advantage of your method over the comparison of two PDFs or two CDFs, similar to the stress strength method?
Yeah, so I would say that what we're doing is very similar to that, in the sense that we're comparing these lifetime distributions. However you want to summarize that, one of the ways we did summarize that was through percentiles. And so that comparison really is like a comparison of CDFs. And I think that the advantage here is that we're accounting for this idea of practical equivalence, this idea of what difference in those CDF values is meaningful to you. Is 1,000 cycles on the toaster meaningful, or sorry, a difference of say 100 cycles of these snubbers, is that meaningful? Maybe, maybe not. Whatever the answer is, though, we're accounting for that in the analysis itself.
Thank you. Oh, it looks like we have another question. So it seems like there might be a final step missing as part of the question. Some way to make a decision on which is better. Could you walk through maybe how you would convince a manager which toaster or spring is better?
Yeah, that's an excellent question. And the methodology as it's presented here sort of intentionally steps away from the hypothesis testing framework because of all of the sort of the misuse and misunderstanding of that, and also the issues of statistical significance kind of being irrelevant when there's a practical importance to care about. And so this really, we can think of it as sort of an exploratory estimation-based analysis. Now, when it comes to actual decision making, I mentioned very quickly early on that how big that probability needs to be is up to the user. So maybe that probability is 0.95, and suiting their own risk tolerance, they say, yeah, and that's high enough for me to be sure that these things are practically equivalent. Or if it's 0.3, that's small enough to say, no, these things are practically dissimilar. One must be meaningfully better than the other. I acknowledge that that's kind of a fuzzy decision process. And as it happens, Christine and Lou and I have done some work recently on trying to formalize that decision framework by comparing your probability of agreement value with a baseline probability of agreement value that you would expect if the two things you're comparing really are true. So that work wasn't done at the same time that this one was, but I think that's sort of the next direction of this whole probability of agreement stuff, is to try to formalize that decision framework.
Great. Are there plans to extend these concepts to more than two groups?
Yes, I would say there are plans. It's definitely on my wish list of things to do. I believe I just saw in quality engineering, like if you go to the like the recently published articles that are just appearing online, I'm pretty certain I just saw someone there do a probability of agreement analysis to compare multiple measurement systems. So people are working on it, people are thinking about it, because I do think that is, I just said the formalizing the decision framework was a logical next step. I would say the next logical step after that is extending this to sort of in general, like a K-group comparison.
Thanks. If POA is, say, 90%, how would you read Snubber to illustrate POA?
Would I read Snubber? I'm not sure I understand that question.
I'm not sure either.
Oh, I see there's a question by the same person lower down. Maybe this is a consecutive thing. So that second one, if the POA is 90% is considered equivalent, what is the reliability of the new Snubber? So I think if I'm understanding the question you're asking, can you look at the probability of agreement plot and sort of backtrack that and understand what the reliabilities themselves are? And the answer there is no. Because your probability of agreement could be a given value. Like if you think about the bathtub shape that we saw, probability of agreement is say 0.75 or 0.9, whatever the case is, 2 times. And so no, I don't think you can sort of back that out and figure out what the reliability is from the POA, from the probability of agreement. The way we like to think about this analysis is that it supplements your other plots. Like all of the examples we went through, we looked at the reliability curves and then the POA. They kind of go hand in hand. It's a way to sort of helpfully interpret those reliability curves.
Thanks. And did you mention where, if anywhere, the prior is input to this and what that was for your examples?
Yeah, I did very quickly. So the way we do the MCMC, the posterior draws are, here it was on this slide, are posterior draws for the betas in the regression. And each of those beta coefficients we assumed had a normal distribution with mean 0, variance 1,000. So very, very diffuse priors. You could change that if you like, and there's another comment here where I acknowledge that in the paper we do sort of a prior analysis study. And depending on the lifetime distribution as well, there are other sort of nuisance parameters. In the Weibull and the gamma, there's a shape parameter that we put gamma priors on, diffuse gamma priors. In the log normal, there's the sigma, the precision. We did a gamma prior on the precision. So you can read about that more in the paper, but that's where it comes in. It's priors on basically the parameters of the lifetime distributions. And then we put that together through this function H that defines this characteristic theta. But as I said, you can read the paper if you'd like. We talk in more depth about these choices and do a simulation study to look at the impact of different prior choices.
Great, it looks like that's all the questions for now. I want to thank Dr. Stevens for his great webinar and congratulate you again for winning the Bisgaard Award. And I want to thank all of our attendees for attending the webinar today. And if you'd like to attend more webinars from the Fall Technical Conference, you can go to the website falltechnicalconference.org and you can find the list of webinars there. Thank you.
Thanks, everybody.